diverse topics from cutting-edge technologies to sustainable solutions. Here we will be featuring eminent young researchers to share their valuable insights for kindling the spirit of future research and development in transportation. Today we have with us Dr. Bhavya Padmanabhan, postdoctoral researcher, National Renewable Energy Laboratory, United States, for sharing her valuable insights on the topic Assessment and Developmental Collaboration Framework for Less-Than-Truckload Carriers. Now, I request Dr. Shalini Yu, scientist, to deliver the welcome address.
Thank you, Ashwati. Good morning, one and all. KSCSTE-NATPAC has initiated the Transpedia Talk Series, a technical discussion platform aimed at fostering research for mutual benefits by sharing knowledge on diverse topics ranging from cutting-edge technologies to sustainable solutions since August 2023. This initiative aspires to create opportunities for young researchers worldwide to connect and collaborate, shaping the future of research and development in transportation. Over the past 2 years, around 25 sessions have been successfully conducted, covering a wide range of topics in transportation engineering. Today marks the 22nd talk in the series, presented by Dr. Bhavya Padmanabhan, postdoctoral researcher, National Renewable Energy Laboratory, United States. It is an honor and privilege to welcome the esteemed speaker, who will share her expertise on the topic Assessment and Developmental Collaboration Framework for Less-Than-Truckload Carriers. Following the presentation, there will be a question and answer session offering you the opportunity to engage directly with Dr. Bhavya. We encourage your active participation in this meaningful exchange of ideas. Thank you once again for joining us. Please join me in extending a warm welcome to Dr. Bhavya as we look forward to her valuable insights. Thank you.
Thank you, ma'am, for the welcome. Now, I would like to invite Dr. Remisha TV, Junior Scientist, to introduce the speaker to the audience.
Good morning, all. Today we have Dr. Bhavya Padmanabhan. Dr. Bhavya is a transportation researcher specializing in freight network modeling, intermodal freight system design, and collaborative logistics. She earned her PhD in civil engineering from the University of South Carolina and later served as a postdoctoral associate at the University of Minnesota. Through these research experiences, she built a strong foundation in analyzing freight transport system with a focus on improving their efficiency, resilience, and sustainability. She is currently a postdoctoral researcher at the National Renewable Energy Laboratory, where she contributes to the development of freight network model that supports national scale effort to enhance logistic coordination, reduce transportation cost, and lower emissions. With this note, I welcome Dr. Bhavya Padmanabhan to this talk series. Thank you.
Thank you, ma'am, for the introduction. Now, I invite our distinguished speaker to deliver the talk. Over to you, ma'am.
Good morning, everyone, and thank you for the introduction. And I would also like to thank Dr. Ramesha for inviting me to this Transpedia talk series. I'll share my screen in a minute. Can you all see my screen?
It's not visible now.
Okay, thank you. Yeah, I'll try.
Yeah.
How about now?
No, not now.
Okay. Can you see my screen?
It's visible.
Okay.
Yes, it's visible now.
Okay, thank you. And currently I work as a postdoctoral researcher at NREL. And however, the presentation today's presentation will be about the work that I've done during my PhD at the University of South Carolina. And this presentation includes this presentation is about Can you hear me?
Yes. Yes, Dr. Bhavya.
Okay, thank you. And I got a message saying that PC disconnected. So today, this presentation is about collaborative logistics, specifically collaboration of less than truckload carriers and how less than truckload carriers collaborate and make more profit, and how collaborative framework can be um, developed, and what are the challenges of collaborative less than truckload carrier collaboration, and how we can address these challenges to accelerate the adoption of collaboration. So I'll start with introduction and background of my study, followed by the motivation, and then I'll explain the the collaborative logistics and the type of collaboration, and then I'll talk about the two research studies in detail, followed by a research summary. So the introduction of e-commerce has changed how a package is picked up, transported, and delivered to the customers. It includes direct delivery. We all get our packages at our doorsteps or wherever we want to. On shorter lead times like same-day delivery, one-day delivery. So, and we have the luxury to return something that we don't like. That creates reverse logistics. And it has also intensified the competition among the logistic service providers, we call them carriers, because the customers seek for faster, cheaper, and better services. And this competitive environment, the small to medium-sized carriers face significant challenges as they're already running on very thin profit margin. And in addition to that, in the US, 20 to 34% of the trucks are running empty. And if they're carrying some loads, on an average, only 57% of its capacity is utilized. So the factors on the left-hand side shows the increase in number of trips due to the increase in demand. And the factors on the right-hand side shows the increase in number of trips due to the inefficient transportation system. So all these factors together contribute to several environmental and social impacts such as higher emission, congestion, and delayed delivery. So this shows that we need new strategies to move goods from its origin to destination. And one of the strategies is logistic collaboration. And before I dive into the details of logistic collaboration, I would like to explain quickly the background and context of our study. So if you consider a supply chain, the major stakeholders of a supply chain are shipper, carrier, and customers. And our focus is from the perspective of a carrier. And the two types of carriers are full truckload carrier and less than truckload carrier. A full truckload carrier carries goods from a single shipper and it moves from one single origin to single destination. And a less than truckload carrier carries goods from multiple shippers, and it may have multiple pickup points and multiple delivery points between its origin and destination. And we specifically consider the operation of less than truckload carriers as it is more complex than the full truckload carrier. And when we consider the operation of a less than truckload carrier, it is broad, and the two extremes are hub and spoke and pickup and delivery. In hub and spoke, there'll be a main hub and several local terminals. And from the local terminals, trucks go pick up goods from the customers and bring to the terminal, and then ships to the main hub, from where it's get consolidated and then ships to the local terminal near to the destination, from where the trucks actually deliver those goods to the customers. So here there'll be a lot of loading and unloading happens, but in the pickup and delivery operation, truck starts from its depot and go to the pickup location and then to the delivery location and comes back to the depot. So in our study, we specifically considered the pickup and delivery operation of less than truckload carriers. And then coming back to the logistic collaboration happens when multiple parties in a supply chain work together and to plan and execute the logistic operation more efficiently. So if we consider different elements in a supply chain, such as shipper, carrier, and customers, and if they collaborate among themselves, it's called as vertical collaboration. And if the elements in the same echelon in a supply chain collaborate, we call it as horizontal collaboration. Since our focus is from the perspective of a carrier, so this is a horizontal collaboration. So we are going to see more details about horizontal collaboration of less than truckload carriers. And you might be wondering, like, these carriers are competitors. So you might be wondering, like, how competitors can collaborate and like make more profit. So I have a simple example for that. Excuse me. So I have a simple example for that. Here there are two carriers, carrier 1 and carrier 2. One is the carrier 1's depot and 2 is carrier 2's depot. So each carrier has 4 pickup and delivery jobs. And this is a pickup and delivery job where the plus sign shows the pickup location and the negative sign shows the delivery location. So the goal of each carrier is to find the optimal route to serve these jobs. And if they are not collaborating, they try to find a route like this. So the red route shows the route of carrier 1 and the blue route and the green route shows the route of carrier 2. And you can see that these routes overlaps. And if they collaborate, they can exchange jobs among themselves and make more cost efficient routes like this. So here you can see that the distance traveled is much less in the collaboration scenario compared to the non-collaboration scenario. So when distance decreases, excuse me. So when distance decreases, total transportation cost decreases and profit increases because revenue is the same. And the increase in profit is shared fairly among the collaboration partners. So there are several potential benefits for LTL carrier collaboration. Distance decreases, um, total profit increases, vehicle capacity utilization increases, emission, empty truck backhaul, road congestion, and noise pollution decreases. And we also have some successful real-world LTL carrier collaboration, such as the Belgian Post and European-based LTL collaboration. So despite all these benefits, the trucking industry, especially in the US, has yet to adopt collaboration on a large scale. So the motivation of our study was to identify the impediments of carrier collaboration and address those to accelerate its adoption. And for any successful collaboration, planning is really important. And we could plan the carrier collaboration in a decentralized way or in a centralized way. So in a decentralized planning, each carrier makes its own decision regarding how they want to collaborate, what jobs they want to outsource to other carriers, and what jobs they want to acquire from the other carriers. So here, only a limited information is shared among the carriers, and each carrier tries to maximize its own profit. Whereas in a centralized planning, a central authority pulls all jobs and make the job allocation decision on behalf of the carriers. So here, send all information on all jobs must be shared to the central authority, and the central authority tries to maximize the total profit of the coalition. The centralized planning has more potential to improve profit. However, there are several challenges to actually adopt the centralized planning because sometimes customer may not be satisfied if they're served by a carrier other than the one with whom they contracted, or sometimes the carriers may not be willing to share their customers' information to other carriers. So the research gap was how to improve the collaboration participation under the centralized planning scheme. So we proposed a new scheme that allow carriers to retain the jobs they want to serve using their own trucks and only retain the rest of the jobs to the central authority. So the research question here is, since it's not a conventional centralized planning, so what's the potential benefit from the new proposed scheme? So that's what we addressed in our first study. And for that, we described or structured our problem like this. So each carrier receives jobs from their customers, and then they can retain the jobs they want to serve by themselves and then release the rest of the jobs to a common pool. And we also assume that they share the retained jobs information to the carriers. And then the central authority allocate all the jobs. Central authority finds the optimal route to serve both retained and shared jobs, and then allocate these jobs to the carriers. And then the carriers just execute the central authority's decision. So we formulated this problem as a mixed integer linear programming model, and with an objective to minimize the total transportation cost. So here we need to find out the allocation of shared jobs to the carriers and also the truck routes to serve all jobs, including the retained jobs. And as I mentioned, we have an assumption here that we assume that carriers share information on their retained jobs to the central authority. If we have this assumption, then the central authority will be able to find the truck routes to serve both retained and shared jobs. And if we don't have this assumption, then the carriers will be finding their own, like the retained routes for their own retained jobs, and the central authority will be allocating only the shared jobs. And as I mentioned, so this is a mixed integer linear programming model with an objective to minimize the total transportation cost. And here the goal is to find the optimal routes to serve all the jobs. And the decision variables are like to match with the decisions to be made. And we also have several constraints that satisfies time window, vehicle capacity, flow balance, vehicle retention. And so this is a variant of the vehicle routing problem, which is known to be an NP-hard problem. So NP-hard problems, to solve medium to large size problems, we need some heuristic or some solution methodology to find near optimal solution or approximate solution. And commercial solvers will not be able to find optimal solution for large size networks. So we developed a solution methodology based on large neighborhood search heuristic. So for large neighborhood search heuristic, we need an initial solution. As you can see here, this is a depot and we have four truck routes. And so this is a feasible solution, but this is not an optimal solution. And for the LNS heuristic, it's a destroy repair solution methodology. So to destroy the solution, we remove some customer nodes from the initial solution, and then we reinsert the solution back into the network in a better position, such that the total profit is improved or cost is minimized. And we repeat this process until one of the stopping criteria is satisfied. So if we randomly remove some customer nodes from the network, the solution may not get improved. So we used a specific method to remove the customer node that's based on the relatedness measure. So we remove the most related customer nodes from the network, and that ensure the profit increase or cost reduction. And for the reinsertion heuristic, we use greedy heuristic, and sometimes the solution might get trapped in the local optima. To avoid that, we used simulated annealing as acceptance criteria. So the first experiment we have conducted was to compare the solution from the developed LNS heuristic with the solution from a Garobi solver. So this is a commercial solver. And for the network size from 18 to 24, we got an optimal solution from the LNS heuristic. And for the network size from 26 to 36, we got a solution that is better than the incumbent solution from the Garobi solver. So the incumbent solution is obtained by limiting the Garobi run for 24 hours. And for the large size networks, that is 38 to 15 nodes, we got a solution, a good solution in a reasonable amount of time from the LNS heuristic. However, the Garobi solver was not able to find a feasible solution within the 24-hour time period. And so the preliminary experiment shows that there are potential benefits from the proposed collaboration scheme, but we were more curious to know like how the benefits changes with the different parameters associated with the career collaboration. So we did more experiments uh, to analyze. So the first experiment was to analyze the effect of network size on cost savings from collaboration. So for that, we considered 7 different network sizes. And for each network size, we considered 15 instances. And as you can see here, so this is the average cost savings from collaboration. So that is 14.6%. And we didn't observe any specific trend as we increase the network size. However, like this is the green line shows the minimum cost savings from among the 15 instances, and the pink line shows the maximum cost savings from the among the 15 instances. And the difference, we call it as range. And we can say that, so since we have like a significant value as range, uh, it says that the spatial distribution of the nodes has an influence on cost savings, and we can also observe that the range decreases as we increase the network size. So that says the effect of spatial distribution on cost savings decreases as we increase the network size. And then we explored the effect of retained jobs on cost savings. And just to recall, like in this new scheme, we allow each carrier to retain some jobs. And so we tested with 5 different percentage of retained jobs. So the 10% means each carrier can retain 10% of their jobs. So as expected, the cost savings decreases as the number of retained jobs increases. But we also observe that like even when the carriers retain 90% of these jobs, we still have benefit from the collaboration. And then we explored the effect of carrier depot locations on cost savings from collaboration. So here we considered 3 different depot locations. And this is actually, this experiment gives an insight into the collaboration partner selection. So this is helpful for the decision makers to analyze, to make a decision on collaboration partner. So here we observe that like when the depot locations are like as the distance between the depot locations increases, then the cost savings increases. And this is true for all the percentage of retained jobs we considered. And then we analyze the effect of overlapping region on cost savings from collaboration. Overlapping region means it's a region where the customers, it's a shared region where the carrier's customers belong to. 100% overlapping means, so this is our study area. It's a 200 mile square by 200 mile square area. So here, this is a common region for all the carriers. So this small red stars represents the carrier depot locations, and all the black dots are customer locations. So here, 100% overlapping means like a carrier can have customer anywhere in this study area. And no overlapping means each carrier has exclusive region where their customers belong to. And overlapping means each carrier has an overlapping region and also has an exclusive region. So we observed that the highest percentage of savings is from the identical scenario where the competition is also the highest. And the smallest percentage of savings is from the adjacent scenario. And in the overlap scenario, the savings actually increases as we increase the overlapping region and also the size of the overlapping region. And the overlapping region and the number of jobs in the overlapping region. And this experiment also gives an insight into the collaboration partner selection, because as we can say here, like there is no point in selecting a carrier as a partner where we don't have like any overlapping region. So in this first study, we proposed a new collaboration scheme for centralized collaborating planning, that is to allow carriers to retain jobs. And we developed mathematical model and large neighborhood search heuristic to solve the problem. And we also found that the average cost savings is 14.6%. However, a lot of factors actually influences the cost savings, such as spatial distribution of the nodes, retained jobs, location of carrier depots, and size of the overlapping region. And the limitations of this study is we didn't consider the individual carrier's profit after collaboration, because that is really important, and it's an incentive for the carrier to join the collaboration. And also we assume that the carriers share information on their retained jobs to the central authority, which is also um, sometimes some carriers may not be interested in sharing their retain jobs information to the central authority. So in this case, this opens up like several questions, and that leads to different methods of collaboration. And that these two limitations we addressed in our second study. So, and if we allow carriers to retain jobs, the two questions are like whether they're willing to share their information on their retained jobs or not. And if they are willing, then the next question is, do they really want to collect the revenue from the retained jobs directly or not? So if they don't want to collect the revenue from the revenue from the jobs that they serve directly, then the central authority allocate the shared jobs to all carriers, and then the central authority distribute the total profit to the carriers fairly. So we call this as method 1, and it's a two-step method. And if they want to collect the revenue from the retained jobs and from the jobs that they serve, then the then the central authority must make sure that the jobs are allowed, and jobs and profits are allocated simultaneously. So we call this as method 2, and it's a one-step method. And if they're not willing to share the information on their retained jobs, then the central authority allocate only the shared jobs and distribute the profit from the shared job. And we call this as method 3, and it's also a two-step process. And the research question here is how much additional profit carriers could make if they're willing to share the retained jobs information. So this is the comparison of method 1, where the customers share information on the retained jobs, versus methods 2 and method 3. And then second research question is how much additional profit carriers could make if they're willing to share the retained jobs revenue. And this is the comparison among between method 1 and method 2. And then the third research question is how much additional profit carriers could make if they're willing to share the retained jobs information but not revenue. This is the comparison between method 2 and method 3. And this is the overview of the mathematical model developed for these three methods of collaboration. And the first method, it's a two-step process. So in the first step, we need a model to allocate jobs. And then the second process, we need a model to allocate the profit fairly to the carriers. So here we use the model developed. In the first step, we use the model developed in the first study. And in the second step, we developed a linear programming model to share the profit. And in the second process, here we need to have a model that can allocate both jobs and the profit simultaneously. And then this method 3, it's the models are, we need two models. One is to allocate shared jobs, and then the second one is to allocate profit. And here these models are modifications of the models from the method 1. So the details are, so that in method 1, we need a job allocation model. So that is the extension of the first study's multi-depot vehicle routing problem with pickup and delivery. The difference is earlier the objective was to minimize the total transportation cost. And here the objective is to maximize the total profit. And the decisions to be made are allocation of shared jobs to the carriers, and truck routes to serve all jobs. And for the profit sharing model, we developed a linear programming model that uses a weighted contribution method. So each carrier gets a profit according to its contribution to the coalition. So the contribution is assessed based on how many jobs are shared to the coalition and how many jobs are served after collaboration. So the objective is to minimize the difference between the contribution based allocation ratios of any two carriers. And in the method 2, we developed a model that can simultaneously allocate jobs and profit. So for that, the objective of this model is to maximize the profit and at the same time minimize the difference between the profit of the most profitable and least profitable carriers. So this is the and this second objective makes sure that the profits are allocated fairly while the job is allocated to the carriers. And here the decisions to be made are allocation of the shared jobs to the trucks or carriers and truck routes to serve all jobs and post collaboration profit of each carrier. And in the method 3, we need again two models, job allocation model and profit sharing model, and both are modified version of the models used in method 1. And here also we compared the solution from the LNS heuristic with the solution from the Garobi solver for both the job allocation model and job and profit allocation model. So this is job allocation model is the model used in method 1, and job and profit allocation is the model used in method 2. Then we compared the total profit from the three methods. So we observed that the profit from the method 1, where the carriers share information on their retained jobs, is always higher than the total profit from the method 2. And the total profit from the method 2 is higher than the total profit from method 3. And this is consistent for all the percentage of retained jobs we tested. Here we considered 9 different percentage of retained jobs and all the different network sizes. And then we calculated the individual carrier's profit and compared that between different methods. So here, like if the carriers are willing to share their information on their retained jobs, then on an average, they'll be able to make 5.6% of additional profit compared to like if they don't want to share their information on their retained. If the excuse me. So this is the comparison of method 1 and method 2. So if the carriers want to collect the revenue from their retained jobs and the jobs that they serve directly, then the carriers will be able to make 5.6% additional profit than method 1, where they don't want to collect revenue from the retained and jobs that they serve directly. And this is the comparison between method 1 and method 3. So here, this is the comparison between the carriers sharing the retained jobs information and not sharing the retained jobs information. So in this case, on an average, carriers will be able to make 12.5% additional profit. And all these small figures shows like the different scenarios, like percentage of retained jobs. And for like in our study, we considered like 3 different carriers, and this is the difference in the profit obtained for all the 3 carriers. And this is the comparison between method 2 and method 3. So this here, each carrier will be able to make 9.45% additional profit, like in method 2 compared to method 3. And the research summary is we addressed a centralized carrier collaboration problem with profit sharing that allows carriers to retain jobs. And we considered 3 different methods of collaboration and profit sharing, and we developed models for all the 3 methods and compare the total profit and each carrier's profit from the 3 different methods. So if the information on retained jobs is shared, then the carriers can expect 0.4% to 22% additional profit. And this big difference is depending upon the several factors associated with the collaboration. And if they're willing to share revenue from the retained jobs, then they can expect 1% to 11% additional profit. And if the information on the retained jobs is shared, but not willing to share revenue from the retained jobs, then they can expect a 0.4 to 14% additional profit. So, and this comparison, this comparison of three different methods is really important because this gives the carriers an idea of like the trade-off between the information sharing or the structure of the collaboration and the profit and the post-collaboration profit. Thank you all, and I'm happy to take if you have any questions.
Thank you, ma'am. That was a nice presentation. Now the forum is open for discussion.
Thank you, Dr. Bhavya, for an informative session. Have few queries regarding, like, first one is, what are the primary challenges in implementing the collaborative strategy in a real world logistics? That's one question. The another question is, beyond cost estimation, like how does this collaborative strategy impact other key performance parameters like transportation cost or emission, environmental emission and all? Did you look into that? That was from my side.
Okay, yeah, thank you. So the real world challenges are mainly the trust issues. The carriers, since they are competitors, they don't trust each other. And if they trust, they have this fear that they might lose their customers somehow. And trust issues is one of the main, and also they are scared to share information about their strategy customers. So that is actually preventing them, or that's actually that's why they're not actively participating or actively not considering collaboration on a large scale. And did I answer your first question?
Yes, please.
Yeah, so and for the second question, like, as I have shown in that small example, like the total distance actually decreases if we utilize the collaboration and, if we plan the collaboration if we effectively plan our collaboration. So if the distance decreases and, so automatically the emission decreases and congestion decreases. It actually and cost decreases. If cost decreases, profit increases. So that is the additional profit. The main thing is total distance travel decreases. So everything is the byproduct of the distance reduction.
Okay, thank you.
So I have a question in the chat. Anso asked, you mentioned that savings decreases as the network size increases. Please explain. I think savings actually the savings does not have, we didn't observe any specific trend on average savings. So it didn't decrease, but we didn't observe any specific trend on average savings. So I don't think it will decrease, but our observation is like we didn't observe any specific trend on savings. Did I answer your question? And so.
Yeah. Yeah, I got the answer, but I was asking from a previous slide of yours. That's okay.
Okay. Previous slide. Is this one? So here, this is the comparison of so this is the comparison of a solution from the heuristic that we developed with the Gurobi solver. So here, actually, it's not to observe like how how the savings, whether it's decrease or increase, like with respect to network size. Here we actually basically compared the solution from the solution that we developed against a commercial solver to understand more about the performance of our heuristic.
Bhavya, this is Samson. Yeah, please, sir. Please,
Yes,
sir.
sir. Yes, sir. Please go on.
Bhavya, this is Samson.
Hi. Hi.
Yeah. It's a continuation of probably the Remisha's question and then Ansu's question. You mentioned that whether this logic is applied in any urban area or cities, something like that, whether it is tried like that, whether it is implemented
not in the United States, but in UK they use a lot of collaboration, for the last mile delivery in the urban area. That is the postal delivery, and in UK they use a lot, but not in United States, at least to the best of my understanding.
Okay, fine. Maybe this is applicable to the city network, but that network must be from a conventional, like a big carrier, the conventional truck or a long truck and all. Then probably the distribution at the city center, probably that network may be working. Okay, I hope that maybe that may be the mechanism there. That.
Yeah.
No? Okay. Fine. Now my question is like probably, but I don't know whether the benefits which you mentioned, like the pollution and the congestion, other things. Now, to what extent, listener, it is practically it is but the benefit which we achieve, I have my own doubt about that one, because the distance travel is maybe the reduction in the distance travel maybe it will be there, but whether it will be very significant, the reduction will be there or not, that may be one reason. Now, thought I'm looking for. Definitely it will be there, but the number of vehicles on the road network or the network will reduce.
If you consider congestion specifically, so this is just a one type of collaboration. So if we consider, for the last mile delivery, like urban area collaboration, so we in UK they have they've been using effectively to reduce the congestion in the urban area. Like when there'll be a consolidation center outside the urban area, and then all carriers bring their goods to the consolidation center and then consolidate, and then actually it's a collaboration, right? So they consolidate and then they'll actually ship 1 or 2 trucks to the urban area. So that's what I mentioned, like in the congestion reduction. So it's used in a wide varieties of way, but this is only a small, particular case that I discussed here. It's a collaboration among less than truckload carriers.
Yeah, fine. That's good. Thank you for that answer. there is a concept in Kerala, in India, especially in Kerala, we have a cooperative concept, a society concept. Like let's say a group of people, they will join together, and then what profit that is coming, that will be shared. That basic concept is like that, and that will be a win-win situation. But the single operators, sometimes they are doing that one. Collectively, when you are looking maybe at the government level or at the semi-government, quasi-government level, if that can be planned, then definitely it will be better. That it will be better. Probably Ansu may be in a position to throw more ideas in that case, like how practical, because he worked in that that area. Thank you for the very good presentation, and and the research and outcomes also very useful for the practical application. Probably the policy makers can use this one to engage that this type of small the distribution network locally, and then probably that can improve the logistical the benefits or the in general. That's what. Thank you, Bhavya, for your.
Thank you so much, sir. Thank you.
Thank you, Dr. Bhavya. This is Praveen from it's a nice presentation. I would like to know whether how the data calculated, like how much and was valid, tested, models was done.
Yeah, for this research purposes, I didn't have any access to real data, so I generated like hypothetical data, and for some instances, I used benchmark instances for the vehicle routing problem, and I randomly generated customer locations and depot locations.
Okay, so like in there, was there any option for getting the real-time data, like even for some sort of validation, or like was the operators willing or something?
I'm sorry. I'm sorry, I'm not able to hear you properly.
Yeah, actually, like for you have done the hypothetical thing. So, like, I'd like to know whether I would try it out for any sort of getting the real-time data to test this out model, so that we can further augment the efficiency of this thing. What the operators, they're willing to share that these details, like etc.
Yeah, definitely. Yeah, I mean, of course, if we have real data, and that actually we can use it to test, but unfortunately, I didn't have access to the real data.
Oh,
and
okay.
they don't, yeah, I mean, the thing is, especially for the, I mean, PhD students, the carriers, they don't share their strategic information.
Okay, fine. Okay.
Yeah. But it would be really good, like, to have a real data to test it out.
Are there any more questions?
Thank you, ma'am. Now I request Dr. Praveen P.S., Junior Scientist, to propose the vote of thanks.
Good morning, everyone. On behalf of NATPAC, I'd like to extend my heartfelt gratitude to each one of you for joining us today for this 22nd Transpedia Research Talk on the topic Assessment and Development of Collaboration Framework for Less-Than-Truckload Carriers. It has been an enlightening and interesting session, shedding light on the core concepts of the collaborative vehicle routing problem with pickup and delivery present with hierarchical models for evaluating collaborative strategies and examine key performance indicators such as cost savings and improving profits. First and foremost, I'd like to express my sincere thanks to our esteemed speaker, Dr. Bhavya Padmanabhan, whose expertise and knowledge have truly captivated our audience. Thank you, Dr. Bhavya, for delivering an engaging and informative presentation. We are grateful for the knowledge and insights you shared with us today. I'd also like to express my gratitude to all the attendees for your presence and active involvement. The questions and discussions that followed the talk showcased your interest in the subject matter, and I appreciate your engagement. Finally, I would like to thank our director, division heads, and the organizing team for their support that made the smooth execution of this program. I'd also like to thank distinguished faculty members and researchers who have joined the talk. I'd also like to thank Dr. Samson Matthew and Dr. Ansu for actively engaging in the discussion. In conclusion, I believe we have all gained valuable insights from today's technical talk, deepening our understanding on collaborative logistics, which is an effective strategy to enhance logistics efficiency and reduce the operational costs. Thank you once again to everyone involved, and we look forward to hosting more engaging technical talks in this series and fostering knowledge sharing through this. Thank you all.
Thank you so much, and thank you so much for inviting me to this talk series, and thank you for listening to my presentation.
Thank you, Dr. Bhavya.
Yeah, thank you.